All right, let's look at the questions from section 3.4. So now we're looking at systems of equations with complex eigenvalues. So how do we deal with those? So first, let's find the eigenvalues of this matrix 2, 2, negative 4, 6. In the same way, so even though we're going to deal with complex eigenvalues, a lot of this approach will be the same as what we're used to. So still set up the characteristic, a minus lambda I as you would. Find its determinant and set that equal to 0. So 2 minus lambda, 6 minus lambda, minus negative 8. So plus 8 equals 0. Lambda squared, minus 6 lambda, minus 2 lambda. So minus 8 lambda, plus 12, plus 8. So plus 20 equals 0. All right, so I don't believe this factors, so let's go ahead and use quadratic formula. Lambda equals negative b, 8, plus or minus the square root of b squared, 64 minus 4 times 1 times 20, all over 2 times a, which is 2. So 8 plus or minus the square root of negative 16 over 2, 8 plus or minus 4i over 2. So 4 plus or minus 2i. Okay, so now we have a pair of complex eigenvalues. Whenever you have complex eigenvalues, they're going to show up in conjugate pairs. One good piece of news about that is because they're guaranteed to show up in conjugate pairs, I only need to look at one. I'll get all the information I need from just one of them. So now I'm going to take 4 plus 2i. It really does not matter which one you take. And I'm going to build this matrix. A minus 4 plus 2i lambda. Sorry, I. So what does that matrix look like? So what is 2 minus 4 minus 2i? So minus 2 minus 2i, 2, negative 4, and then 2 minus 2i. So as I said in the previous section, when you're dealing with complex eigenvalues and you build this, like once you find your eigenvalue and you make this matrix A minus lambda I with the specific lambda that you found, more often than not, at least for me, I suspect it's going to be true for many of you, it's not obvious that what I have here is a linearly dependent matrix. So to confirm, I'm going to take the determinant, minus 2 minus 2i times 2 minus 2i plus 8. And hopefully that equals 0. So minus 4 minus 4i plus 4i. So my imaginary components cancel, which is good news. Plus 4i squared plus 8. So 4i squared is going to be the same as negative 4. Okay, so confirmed that I got the eigenvalue I wanted. It does to this matrix what I wanted it to do. So now what do I do with this eigenvalue? So in reality, I build my solution in the same way, or in a very similar way. So what is x of t going to be equal to? I can't get there yet. I got to get an eigenvector. I'm sorry about that. So from this matrix, now that we've confirmed that it's linearly dependent, I'm going to go ahead and take one of the rows. Doesn't matter which one. So minus 2 minus 2i times x plus 2y equals 0. I'm noticing that everything has a coefficient of 2, so I'll divide the whole thing by 2. So negative 1 minus I times x plus y equals 0. Y equals 1 plus I x. This gives me a good eigenvector. If I let x equal 1, then y would have to equal 1 plus I. So this is a good eigenvector. So now what do we do with it? X of t is going to be equal to, for right now, I'm just going to say capital C times what though? The first component of my eigenvector is 1 times e to the lambda t. What's our lambda? The lambda we chose is the positive one, 4 plus 2i t. So what happens when I raise e to this complex number times t? Well, it breaks apart into these two pieces. So c times e to the 4t times e to the 2it. E to the 2it can be further broken down from an Euler identity. So c e to the 4t times cosine 2t plus I sine 2t. So we have imaginary operators in here. We are solving a system of equations that only has real values and real coefficients. So because of that, our solution needs to have real values and real coefficients. So in general, our real solution is going to look like this. X of t equals C1 times the real part of, actually, so C1 times the real part of this general solution. So while we're saying that, what's the real part? The real part is going to be e to the 4t times cosine 2t. So C1 e to the 4t cosine 2t. What's the imaginary part going to be? So plus C2 times the imaginary part. So C2 e to the 4t sine 2t. And I think I've said this before when we were last focusing a lot on complex numbers. The imaginary part of any complex number, think of that like a magnitude. Think of that like, the degree to which it is imaginary. But since we described that as a magnitude, the imaginary part of a complex number is a real value. So another way to kind of emphasize that our solution needs to have real coefficients in it, only real numbers, which this fits now. So what is our y of t going to look like? Basically, we're going to build the same thing, except now we're going to be working from the second coordinate of the eigenvector. So this case, the x case, was relatively simple because the x coordinate of that eigenvector was 1. Now what I have to think about is this. I'm going to multiply everything that I come up with times 1 plus I. Still multiplying it by e to the 4t times the quantity cosine 2t plus I sine 2t. My y of t is still going to equal this. It's still going to equal C1 times the real part of the solution plus C2 times the imaginary part of the solution. So now let's think about this. If I were to multiply this binomial 1 plus I by this binomial with the cosine I sine, what is going to be real? One part that's going to be real is this. So e to the 4t. 1 times cosine 2t is going to give me a real value. But so is I times I sine 2t. That gives me I squared sine 2t, which is equal to minus sine 2t. So that's the real part. The imaginary part is going to be C2 e to the 4t. And what's going to be imaginary? I times cosine 2t, that'll be imaginary. So cosine 2t. And 1 times I sine 2t will be imaginary, so that'll be plus sine 2t. So this is my general solution. Here's my x, here's my y. All right, that's all for question 1. Question 2, same, most of the process here is going to be the same, except now I have an initial condition to help me find the values of the constants that I was unable to evaluate in the last question. So what's our first task here? Build out the matrix that I need. So 2 minus lambda times, or negative 5, 1 minus 2 minus lambda. The determinant of that is going to be 2 minus lambda times minus 2 minus lambda minus negative 5, so plus 5 equals 0. All right, so I'll get lambda squared plus 2 lambda minus 2 lambda minus 4 plus 5. So lambda squared plus 1 equals 0. Lambda squared equals negative 1. Lambda equals plus or minus I. Just like last time, I'm going to stick with only one eigenvalue because it tells me everything I need to know. I'll stick with the positive one, but it really doesn't matter. You can take whatever one you want. You're going to wind up in the same place if you do everything correctly. So my new matrix is going to be this: 2 minus I minus 5. 1 minus 2 minus I. Now I want to make an eigenvector from this. I'm going to take the bottom row this time because it has smaller coefficients. One of them is a 1, so hopefully that's convenient. So I get 1x plus minus 2 minus IY equals 0, or x equals 2 plus I times y. So a good eigenvector would be this. If I make y equal to 1, and then x equal to 2 plus I think that's a fitting eigenvector. So now that I have my eigenvalue and eigenvector, I can do everything I need to do. So x of t is going to be equal to c1 times my eigenvalue, or no, not times the eigenvalue, times the x-coordinate of my eigenvector, which is 2 plus I, times e to the power of lambda t, so e to the it. But what is e to the it? There should be an equal sign in here somewhere. X of t equals this, which is equal to c1 times 2 plus I times, no e term because the e to the it is totally imaginary. There is no real components of that exponent. So cosine t plus, move, I sine t. So same approach as before. I would like to, I'm just going to call this positive, just big capital C for now. I want to break this down into its imaginary and real components. So what's going to be real here? C1 times 2 cosine t plus I squared sine t. So 2 cosine t minus sine t plus C2 times the imaginary stuff. So I times cosine t, so cosine t plus 2I sine t, so plus 2 sine t. So there's a good solution for x. What's y going to look like? Y of t is going to equal big C times the y-coordinate of my eigenvector is simply 1 times e to the it again, so that'll be cosine t plus I sine t. So now plucking out the imaginary part and the complex, or the real part and the complex part will be simpler here because my eigenvector only has, one term in it. So yt equals c1 times the real part, so cosine t, plus c2 times the imaginary part, which is sine t. All right, so I have my general solution for x of t and y of t. So now we can use the initial conditions. So x of 0. What happens when I plug in 0 for all my t values in here? I get c1 times 2 times cosine of 0, which is 2, minus sine of 0, which is 1. So 2c1 plus c2 times cosine of 0, which is 1, plus 2 sine of 0, which is 0. So plus c2 times 1 equals 2. And then y of 0 equals c1 cosine of 0, which is c1, plus c2 sine of 0, which is 0. So c1 equals 1. So I got one of them for free. If c1 equals 1, then I get this from this top equation. 1 times 2 plus c2 equals 2. So that looks like c2 equals 0. All right, if c1 equals 1 and c2 equals 0, what is our final result here? X of t equals 2 cosine of t minus sine of t plus c2 times 0. c2 is 0, so that's all that remains. And y of t equals cosine t. So this is all that remains for our solution based on that initial condition. All right, moving on to 14. Got another initial value problem. So let's go ahead and rapidly find those eigenvalues. So minus 7 minus lambda, 13 minus 2, 3 minus lambda. The determinant is minus 7 minus lambda times 3 minus lambda minus negative 26 equals 0. Lambda squared minus 3 lambda plus 7 lambda minus 21 plus 26 plus 5 equals 0. Quadratic formula, because we have assumingly going to have complex eigenvalues. Lambda equals negative b plus or minus the square root of b squared minus 4 times 1 times 5 all over 2. So I get negative 4 plus or minus the square root of negative 4, so 2i over 2. So minus 2 plus or minus I. Again, I'm going to take the eigenvalue that has a positive I in it. So when I do that, what matrix do I get from here? So A minus 2 plus I, capital I. This gives me, so minus 7 minus 2 is minus 5 minus I, 13, and then minus 2. 3 minus 2 is positive 5 minus I. Okay, I'm going to take the determinant here because, again, I just want to be very safe. I want to make sure that the matrix I found is actually singular. So minus 5 minus I times 5 minus I minus negative 26, so plus 26. All right, so negative 25 minus 5i plus 5i plus I squared plus 26. So minus 25 minus 1 plus 26 equals 0. got the matrix I wanted. So now that I have the matrix I wanted, what should I do with it? We should make an eigenvector out of it. So I will take the bottom row because it has smaller coefficients. So negative 2x. Actually, I take it back. I'm going to take the top row because if I do some moving around of objects, I can get all positive numbers. So minus 5 minus I times x plus 13y equals 0. So then I get 5 plus I times x equals 13y. I'm going to go ahead and stop there. An eigenvector I can make is basically if I switch the coefficients. If I multiply 13 times 5 plus I and multiply 5 plus I times 13, those will equal. So I'll make x 13 and y 5 plus I. So now that I have this eigenvector, what should we do with it? Let's build out the solution. So x of t is going to equal to capital C times 13 times e to the lambda t, so that's minus 2 plus it, which is equal to c times 13 times e to the negative 2t e to the it. Which is equal to 13 capital C e to the negative 2t times this quantity, cosine t plus I sine t. All right, so now that we've decomposed that, we can start thinking about where the real and the imaginary components will wind up. I'm multiplying by a real number, so the imaginary and the real components are not really going to change hands. So what I'll have here is this, 13 C1 e to the negative 2t cosine t plus 13 C2 e to the negative 2t sine t. All right, so that's x of t, the general solution for that. So now let's deal with y of t. Y of t equals capital C times 5 plus I times e to the negative 2t times cosine t plus I sine t. All right, so now we can break up the real and imaginary parts. So C1 times the real part. That'll be 5 cosine, nope. There's also an exponential. So C1 e to the negative 2t times 5 cosine t plus I squared sine t, so minus sine t, plus C2 e to the negative 2t times the imaginary part, which is going to be I times cosine t, so cosine t, plus 5I sine t, so plus 5 sine t. So we're done with our general solution for both x and y. So I can use the initial conditions now to figure out what these constants are. So x of 0 is equal to 13c1 plus 13 times 0 because there's a sign there. So 13c1 equals 1. So c1 equals 1/13. What about y naught? Y naught is equal to c1 times 5 cosine t. So 5 c1 plus c2 times 1. So 5c1 plus c2 equals negative 1. But we just found out that C1 is 1/13. So 5/13 plus C2 equals -1. And I think that means that C2 is equal to -13/13 minus 5/13, so -18/13. All right, so all told, go back. We can drop in those constants. So C1 is 1/13. C2 is -18/13. So then, running out of space, let's try. What's x of t? X of t equals 13 times 1/13. So e to the -2t cosine t plus 13 C2. So that's -18 e to the -2t sine t. Y of t is equal to C1. Let's just try to do this all in one shot. Let's group all the cosines and sines together. So you're going to have C1 times 5. So 5/13 cosine from the first term, and then C2. 5/13 cosine minus 18/13 cosine. So that's minus 13/13. So you get minus e to the -2t cosine t. And now what about the sines? C1 is 1/13 times -1. So -1/13 sine of t. C2 is -18/13 times 5. -18 times 5 is -90. So -90 minus 1, that's -91/13, which is exactly 7. So minus 7 e to the -2t sine of t. So at long last, that is our solution for this system. And that is all for section 3.4.